Hello everyone, my name is Luis and I will be talking about supersymmetric dark matter. Let's start with what dark matter is. We don't understand a whole lot about dark matter, but for the most part we know that it makes up about 80% of the mass of the universe. Because we don't know a whole lot about dark matter, there have been a lot of propositions trying to understand what dark matter could be. One of those is called the minimal supersymmetric standard model, the MSSM. Now, the MSSM introduces new cousin particles of those particles in the standard model. The picture below gives you a cartoon representation of what the MSSM sort of looks like. Now, we believe there is a supersymmetric particle called the neutralino, more specifically the lightest neutralino, as a prime candidate for a dark matter particle. The reason we believe this is because since it is the lightest supersymmetric particle, it cannot decay into anything else, meaning it is also stable. Now, how do we detect a dark matter particle? Well, let's start with a simple case of particles annihilating. If you look at the figure in the center, there is an electron and a positron. These two particles can collide into each other, and after the collision, photons are produced. This is essentially what is happening in the figure below with B quark and B antiquark, but it's a little more complicated. In this annihilation, we have two dark matter particles annihilating into each other, releasing some photons during the annihilation, then creating two final state particles, B quark and B antiquark. But these particles aren't stable, so they'll decay and release photons during the decay. Now, the best place to detect these dark matter particles are through dwarf satellite galaxies because of their incredibly low background in photons. Now, neutralino dark matter doesn't just annihilate into one type of final state particle. It can annihilate into a variety of final states. For example, two neutralinos might annihilate with the following: 44.9 into W's, 37.3 into Z's, and 9.51% into BB bar. Now, these particles are particles in the standard model. They are not particles of the supersymmetric standard model. The tool I use to create these plots is called MADHAT, Model Agnostic Dark Halo Analysis Tool. MADHAT holds 58 dwarf galaxies, which are all pre-processed from the Fermi-Lab telescope, which also allows us to analyze photon data from these dwarf galaxies. Using MADHAT allows me to place limits on the cross-section for any annihilation channel, and it does this through a few equations: the expected number of photons from dark matter annihilation, and it uses the quantity phi pp, which is based on the dark matter particle physics model. Now, if we look over at the graphs in the center, here I consider 24 dwarf galaxies. Applying the dark matter annihilation channels from these benchmarks, we can then compare the limits on the predicted cross-section from each benchmark point to see if the point is excluded or not. Now, we can see that one model is excluded in dark red on the right graph. We have several others that are close to predicted cross-section, but as it stands right now, with more data and increased sensitivity of the Fermi-Lat, our ability to discover or exclude dark matter models grows. That's all I have for you today. Thanks for watching.